Hi, everyone. I'm James Duong, and I'll be presenting today with David Lee to talk about Flight SQL, a new wire protocol for accelerating database access powered by Apache Arrow. So Flight SQL is a new wire protocol that we've implemented in the past year or so for accessing SQL databases through a technology built into Arrow already called Flight. It's a high-performance protocol initially powered by gRPC that sends Arrow data directly over the wire without any serialization. So the data is already columnar, and it doesn't do any sort of transposing of the data to make it compatible to get it to a row-oriented format. What Flight does is adds extensions to Flight to standardize how certain operations are done, like how do you execute queries, and how do you get database metadata, and how do you request information about database capabilities. So why do you need Flight SQL? Well, with Flight SQL, we have a standardized protocol to do columnar transport. Columnar transport, it tends to be more easily compressible due to how data is arranged to be more similar. More similar data. Data is arranged such that more similar data is grouped together, making it easier to compress. Aside from that, there's no need to transport the data from a columnar format to a row-oriented format, and there's no need to serialize the data to a different format than Apache Arrow. So if you have an Arrow-aware client, you can consume data right off the wire without having to deserialize it. And what this does is it gives us a 20x performance speed up over ODBC when we were trying it out with Tremio. An aspect of Flight that Flight SQL takes advantage of is the ability to partition data across different servers and allow clients to consume the data in parallel. So a Flight SQL client application will send a query to the server, and the server is allowed to tell the client, hey, I have parts of my data hosted on this DB node. I have parts of my data hosted on this second node. I have another part of my data hosted on this third node, etc. And the client is allowed to consume this data in parallel. Note that the client itself can be like a multi-process application, like Apache Spark, for example. So we leverage this built-in feature of Flight to enhance database, the ability to consume data from databases. What's great about Flight SQL is that it's database agnostic, for starters. Any Flight SQL server will work against drivers that have been built, Flight SQL client drivers, which are available currently in Java and C++. What this means is that if you write an application using a Flight SQL driver, you can make it work with any Flight SQL database, regardless of what the backing database actually is. So for example, I could write a program that reads data I could write a program using a Flight SQL client and have it read data from, say, Oracle or SQL Server or Postgres or Dremio without having to change the code or download a different driver. The same driver works against all these databases, provided they support a Flight SQL front end. This is similar to how some popular databases implement the Postgres protocol to have compatibility with Postgres applications and the Postgres ODBC and JDBC drivers. For example, Amazon Redshift supports the Postgres protocol, and so does Vertica, and they can be used with Postgres-based tools. It's the same idea. A Flight SQL tool can work against anything that supports the Flight SQL protocol.
So Flight SQL builds on top of Flight. So let's dig a little deeper into what Aeroflight provides for Flight SQL. Aeroflight is an RPC framework. It's a sub-project of the Apache Aero project. And its main distinguishing feature is that it's specialized for working with Aero data. What this means is that it can optimize for Aero data and avoid unnecessary data copies between the application and the underlying network transport. On top of that, it also actually abstracts away the underlying network transport so that you can use different libraries for different use cases. Most flight implementations are built on top of gRPC, an RPC framework from Google, but there's experimental support for different network transports in C++, which currently lets you also work with UCX, which can be useful if you're working with something like an InfiniBand transport. Aeroflight itself is supported in multiple languages, including Java, Python, Go, C++, Rust, and C#. So you have your choice of implementation language when you're working with Aeroflight. So I mentioned Aeroflight is a specialized RPC framework. What this means is that Aeroflight actually predefines all of the available RPC methods. It provides some for reading and writing Aero data. For example, in this diagram here, there's a method called doGet. A client that calls doGet on a server gets back a stream of Aero record batches. And because this is a predefined method, the Aeroflight implementation can optimize this to make sure that we're not copying data more than is necessary. Aeroflight also predefines methods for working with metadata or things that aren't Aero data. And combined, this means that you can build your application semantics on top of Aeroflight's predefined RPC methods. You don't have to deal with Proto-C or code generation like you might have to when you're working with gRPC directly. You can just import Aeroflight and start building your application. So what are the kinds of optimizations that Aeroflight implements? Let's look at how things work when you aren't using Aeroflight. Say you want to combine Apache Aero with protobuf and gRPC. Of course, gRPC is a fairly common RPC framework, and protobuf is generally used alongside gRPC as the format for the messages. So in this case, to send some Aero data, you'd have to take the Aero data and serialize it into a byte buffer so that it can be placed into a protobuf data structure. That's already at least one data copy, possibly two, depending on how your protobuf library works. Then when you give that protobuf message to gRPC, gRPC is going to serialize all of that data again to get a byte buffer from the protobuf message. So we have at least two data copies here that are frankly completely unnecessary. Aeroflight hooks custom serializers into the underlying network transport so that we can directly generate the final network payload as if we ran the protobuf serializer without actually having to use the protobuf library. So effectively, we can directly hand the Aero data to gRPC along with some synthesized metadata to make it look like a protobuf message without having to actually copy all of the Aero data, which saves you memory and CPU cycles. So Aeroflight SQL just builds on top of Aeroflight. It fills in the blanks, so to speak. It defines any protocol, request, and response payload messages that are necessary, and it tells the application what the sequence of RPC calls it should make. So let's look at an example of executing a query with Flight SQL. So Flight SQL client is going to call a flight method on the Flight SQL server. Actually, we can color code this to distinguish between the two. So Flight SQL client is going to start by calling a method called getFlightInfo. It's going to provide a request payload that's been defined by Flight SQL, which effectively just encodes the SQL query. The Flight SQL server is going to respond with a flight info message, which is just defined as part of the base Aero flight. Flight info contains a list of endpoints, which are all of the servers that the client needs to talk to in order to fetch all of the Aero data for the query. So this is where the distributed execution concept that James described comes into play. A server can choose to just respond a single endpoint if the data is just on the same server or on a single server, or it can choose to respond with a whole list of endpoints if the data has been partitioned or distributed across multiple workers. The Flight SQL client can then go fetch each of those endpoints to get the actual arrow data, to get the actual arrow data as a stream of arrow record batches. So here the client can choose to fetch all of the data in parallel on a single node, or if the client itself is distributed, again, say it's something like Apache Spark, then the client can distribute those endpoints among its workers and fetch all of the data in parallel across multiple machines. So for more details, you can look at the Aeroflight SQL documentation, which contains other sequence diagrams that explain different scenarios and different request response patterns.
So the Aeroflight SQL project has been accepted and merged with the Aero project already. It's marked experimental, but it's ready to use. What's coming up next is a JDBC driver that built on top of the Flight SQL Java driver. The purpose of this is to handle a case where we have countless Java applications that are built using JDBC. It may not be feasible to update all of these to use Flight SQL immediately. So we provide a JDBC driver to bridge the gap between a legacy JDBC application and a Flight SQL server. So this is a new JDBC driver that's in a public PR right now that will let you connect any JDBC application to any Flight SQL server, be it a server for Dremio or SQL Server or Postgres. This will let you hook up any program such as Tableau or DataGrip to it. This driver was built by Quill Technologies and Dremio, and is currently under review. What this driver does is it lets a legacy application benefit from the high performance Arrow protocol without needing to be rewritten.
So given that, you might wonder why Flight SQL didn't choose to build on top of JDBC or ODBC in the first place. So there are a couple reasons why. First one is just, again, Flight SQL is more of a wire protocol for columnar databases, albeit one that can also directly be used by a client application. But that means that it's not necessarily directly in competition with APIs like JDBC and ODBC. Instead, it's also intended to just help. It's lower level. It provides a concrete wire protocol and concrete client and server libraries. So it helps implementers of databases and applications. But in that respect, again, as James mentioned, you can kind of think of Flight SQL as an alternative to how other databases just do things like re-implement the Postgres wire protocol to benefit from existing Postgres clients. But again, also, because Flight SQL is built on top of Arrow and Aeroflight, it integrates into the Arrow ecosystem and tooling. It benefits from things like the minimal copy design and zero serialization design in Aeroflight. And it means that it integrates more easily with other Arrow native applications and tools and other libraries around the ecosystem, like pandas that work with Arrow already. Finally, JDBC and ODBC are large and complex specifications to build on top of, and they present a large implementation burden for databases. Flight SQL, being more minimal, can be easier for databases to implement. Also, these existing specifications have the problem that they're often inherently row-based and often also focus on transactional use cases. So while we could try to extend these protocols or these specifications for columnar and analytic workloads, that would effectively be creating a completely new API. And so in that case, there was no reason to try to keep all that existing baggage when we can instead start fresh and focus on the workloads that fit best for Arrow. So if you're interested in Arrow Flight SQL, here's how to get involved. So if you want to just use Arrow Flight SQL, like James mentioned, it's already a part of the Apache Arrow libraries from version 7 onwards in C++ and Java. If you have questions or want to propose enhancements or just want to show off something that's built on Flight SQL, you can join the Arrow mailing list and talk to other developers there. In fact, just a few days ago, a developer wrote in showcasing a Spark SQL based implementation of a Flight SQL server, meaning that you could use Spark SQL to execute SQL queries over Flight SQL. So if you have a project like that, we'd also be interested in seeing that. There are also a few related projects in and around the Arrow ecosystem that you might be interested in if you're also interested in Flight SQL. One is Substrate. Substrate, which you can learn more about in other sessions at this conference, is a common serialization format for relational queries. Or in other words, it's kind of like an IR for different SQL dialects, and also for libraries like dplyr or IBIS. There are discussions about adding support for Substrate in Flight SQL, so that you can talk to a database both with SQL queries and with Substrate queries, which would give you a universal query language to go with your universal columnar wire protocol. There's also a proposal called ADBC. So as the name implies, ADBC intends to occupy a similar space to JDBC and ODBC, although it's also not directly trying to compete with them. The problem that ADBC is trying to solve is we have Flight SQL, but we also already have other existing wire protocols for columnar databases. For example, BigQuery already implements its own gRPC-based protocol. ClickHouse implements its own protocol. DuckDB has its own C API, and so on. ADBC intends to try to abstract. ADBC wants to be able to abstract across these different protocols, so that clients can just write to a single API without having to worry about the underlying wire protocol. In much the same way that a client using JDBC or ODBC doesn't have to worry about writing database-specific application code for each of their databases. So if you're interested in that, that's also being discussed on the Arrow mailing list. So thanks everyone for listening, and I hope to see you around the Arrow mailing list or in the Arrow repository as well.